So hello students, welcome to our YouTube channel. Please do like and subscribe, like the video and subscribe the channel if you really find these questions to be helpful for you people. So these are the two questions for today, the questions of permutation and combination. So you might be thinking that why did I take up two questions? I mean, we normally take one question at a time, no? See, both questions are based on the same concept, and for me, according to me, this concept in permutation and combination is extremely important, and the concept is of principle of inclusion and exclusion. So both the questions are related, though they are two totally independent question, but when we will take it up with the help of that concept, that expression, I will tell you how to find answer of this one. Okay, so let's start. So the first question is 7 balls are to be put in 4 distinct boxes such that no box is empty. Find number of such ways. Okay, so of course if nothing is said, we will assume the balls to be distinct. Okay, so assuming the balls to be distinct, so again I am repeating, if nothing is said, then we will assume to be distinct. Okay, so 7 distinct balls are to be put in 4 distinct boxes such that no box go empty. Okay, so no box go empty. Now what do we do? So I think we have already discussed the principle of inclusion exclusion. We have solved 1 or 2 questions also earlier. Now today we will be using it two times in the same video. Okay, now see, first one is these are 4 boxes and we have to distribute 7 distinct balls in these 4 distinct boxes, and the condition is no box should go empty. Now all possible ways of putting 7 balls in 4 boxes without any restriction. So what are those possible ways? So total number of possible ways are, see, every ball has 4 choice. You pick up a ball, you have 4 boxes in front of you. You can drop it in any box. Pick up second ball. Again, there are 4 boxes in front of you. You can drop it in any box. So every ball has 4 choices. So 4 into 4 into 4, how many times? It's 4 raised to the power 7 times. Now from here, I will be excluding those cases when at least one box go empty. So when at least one box goes empty. So at least one box. So what will I do? To ensure that at least one box is empty, I will select one box out of 4. Let's say I selected this box. 1, 2, 3, 4. If I keep that thing in my mind, this is first, second, third, fourth box. Okay. So I am selecting one box out of 4 boxes. And how many ways we can select 1 out of 4? 4 C1 ways. Now you have just 3 choices for every ball. So you pick up a ball, how many boxes you are having to put a ball in that box? So you have just 3 boxes available now. So 3 choices for every ball. So total number of ways of putting balls in the boxes are 3 raised to the power 7. Okay, now what happens is whenever we do calculation for at least and we are making a selection in such cases, okay, there will be a repetition. I will explain you how. See, let's say, see, 3 raised to the power 7 balls. Ways, 3 raised to the power 7 ways. Doesn't that include that way when we put all our 7 balls in box 4? Accepted or not, bacho? Because 3 raised to the power 7 means unrestricted way. I removed one box empty to ensure it is empty. Rest there are 3 boxes. Okay, so that include a way when we are putting all balls in 4th boxes. What does that mean? That means box 2 and box 3 are also getting empty. Okay, now it is a case when in 4C1 way we select 3rd box and keep it aside, and you have 3 choices for every ball, box 1, box 2 and box 4, and again you put all the balls in box 4. So again these 3 boxes are empty. So again like that way you have one more case that you select second box in 4C1 ways, 1 way is to select second box and keep it aside, and then again in 3 raised to the power 7 way it will have a way when you put all your balls here, that means this box is again empty. So we are counting the case when box 1, box 2, box 3 empty 3 times when we are writing this expression. Am I clear? So what I mean to say here is, what I want to say here is that there will be repetition of so many cases. 2 box empty cases, there will be so many repetition. 3 box empty cases, there will be repetition, as I showed you. Okay, so what happens is then we will be from this, actually what happens is from this we exclude, because there are repetition when 2 boxes goes empty, we will exclude those cases when at least two boxes are empty, when at least two boxes are empty, and then all possible choices are 2 raised to the power 7. And then again, see, try to imagine again. Okay, let me try to explain here. When two boxes are empty, I remove first and second box. Okay, then again, out of 2 raised to the power 7 ways, there is one way. When you put all your balls here, third box automatically go empty. And similarly, out of 4C2 ways, there is a possibility that I select which box I selected, first and second. I select second and third, and then again I put all the balls here. Then again these 3 boxes are empty. So see, every time you are writing at least case, the next step cases are being included many times. They are repeated many times. So from here, actually what happens is, in this you will be excluding those cases when at least 3 boxes are empty, and that's the last possible case. Isn't that? Why? Because if you put or keep all the 4 boxes empty, you don't have any choice for putting any ball in any box. Okay, and there's only one choice for every box. You need to put it in the 4th box or the last box remaining all your balls. Okay, now if you remove your bracket here, so that gives us the principle of inclusion and exclusion. So minus, and then it becomes positive 4C2 2 raised to the power 7. 3 minus makes it negative 4C3 into 1 raised to the power 7, and it ends at 0. It ends at 0. So okay, so how we I interpret it: include all the cases, exclude when at least one is empty, then include for 2 boxes, at least 2 boxes are empty, and then exclude at least 3 boxes are empty, and then include when all the 4 boxes are empty. So that's the principle of inclusion and exclusion, bachcho. Okay, so write all possible cases: minus when at least 1 box is empty, plus 2 boxes are empty, minus 3 boxes are empty, plus 4 boxes are empty, and you can continue and proceed till you reach your last term, which ends at 0. Okay, so that's the series here. Okay, so that's the answer. Okay, you can match it. You have different another way of doing it also. Okay, with the help of distribution, grouping, and then you can do it. Okay, if I give you a hint for that, so that is like 4 boxes means you have to distribute 7 balls in 4 parts such that none is empty. So the 1 is 4 1 1. In how many ways you can form this grouping, since all the objects are distinct? Okay, so in how many ways you can get it? 7 factorial by 4 factorial, and there are 3 identical size groups upon 3 factorial. Okay, and then you have like what are other possibilities? So 4 1 1 1, that is 7, and then if I include here 5, you can't take 5. So 3 3 1 not possible, 3 2 2 not possible, 1 1. That's one case. So 7 factorial by 3 factorial into 2 factorial, and 2 identical size, one object each. So for that 2 factorial. Then 3, is there any other possibility, bacho? 3 1 1 not possible, 4 1 1 1 done. So let's start with 2 then. 2 2 2 1. So 7 factorial by 2 factorial cube, and then 3 identical, so into 3 factorial. Okay, is there any other possibility? So like that you have to count the cases, and then you have to distribute. Like these are the ways of grouping 7 balls into 4 groups such that each group has at least 1 ball, and then you will be distributing it in 4 factorial ways among 4 persons. Okay, see, identical size group doesn't mean groups are identical till the objects are distinct. Groups will always be distinct. It doesn't matter whether the size are identical or size are distinct. Okay, so that's it. Similarly into 4 factorial. So here you need to count the cases. Though you can do it, I mean that's not that difficult. We can do it. Is it possible that we don't have any other case? I think that's it. We don't have any other case. Okay, one without one we can't do, because we need at least 2, 2, 4, 6. Now, I think these are the 3 cases. Then you count it and match your answer, bacho. Okay, so that these are 2 ways, but my focus was on like principle of inclusion and exclusion. Now look at this question, bacho. Look at this one. 75 raised to the power 50 minus 75 C1 into 74 raised to the power 50 plus 75 C2 73 raised to the power 50 minus 75 C3 72 raised to the power 50. See, that seems to be a question of binomial, but to be true, I tried it two, 3 times, but I couldn't solve it with the help of binomial. Okay, every time I get it, then I just go to principle of inclusion, exclusion, I get the answer. But using binomial till now, I couldn't solve it. So if anyone has that idea, let me share it with me so that I can just go through it. And if it's really, I mean, that's correct, then I will definitely appreciate it. Okay, and keep it also for myself. Okay, but see, how do I do it? If you compare this expression with this one, bachcho. 4 raised power 7. See, this number is constant throughout. This number is not changing anywhere. And the base of these terms are reducing one by one in every term. Okay, and it starts with 4C1, 4C2 every time. Now compare. So power is 50. It's not reducing in any term. Base is getting reduced one by one in all the terms. And then 75C1, 75C2, that's fixed with the number we started. Okay, now if you compare it, so here you had the base or the superscript of NCR. Those were the number of boxes and the constant power were the number of balls. So if you compare it, that means I will say let there be 75 distinct boxes, bachcho, and 50 distinct balls. So, if I ask you in how many ways you can distribute balls in boxes such that no box is empty, what's the expression you will write? You will write, okay, first ball has 75 choices, second ball 75 choices. So, all possible choices are 75 raised to power 50. Then at least one box goes empty, 75C1, and then total choices are 74 raised to power 50, and that's it. So, this is the expression when I have to write the expression for the case when I have to distribute 50 balls in 75 boxes such that no box is empty. But tell me, you have lesser number of balls than the number of boxes. Is it possible that no box is empty? Answer is no. So whatever happen, whatever come, but this answer will be 0. There is no way in which you can distribute 50 balls in 75 boxes so that no box is empty. So that was the relation of this series with your principle of inclusion and exclusion here, bachcho.